All right, folks. Today, we're going to talk about recursion. This is essentially a process that sort of acts like a loop. You can sort of do things sort of over and over again to accomplish whatever sort of goal you want. Oftentimes in sort of beginning CS classes, and sort of specifically at some other universities, rather than starting with loops, recursion is sort of an idea that's sort of a CS1 topic, and sort of use recursion throughout sort of an entire semester. That's not quite the way that we do it here. Obviously, you saw loops in CS1. We've been using loops throughout CS2 as well. And I'm not going to spend a ton of time on recursion, but I want to give an idea of what it is and sort of how to approach using recursion in maybe code that you might come up with in the future, or if you see code that uses recursion, you'll at least understand that that's what it's doing. So just as sort of an exercise first, let's write a factorial. So this is just sort of the math formula for it, but the sort of uppercase pi here is a product. So essentially, we're having a situation where if we put in like 5 factorial, that's going to be 5 times 4 times 3 times 2 times 1. That will give you the 5 factorial, which I think this is what, it's like 120 or something. We go from this sort of k equals 1 to n, and we multiply. So our sort of k equals 1 would be this one, and then we go k equals 2, k equals 3, k equals 4, k equals 5, and they're all a product together. So think of it, like a sum. Sum uses a capital, sort of a capital epsilon. But the product is a capital pi, and it's just like the sum, except we're using multiplication. Clearly, you could write this as a loop, just like we could write any sums as a loop. We could write any products as a loop. So let me show you how to do that, and we'll just do it with a loop, and then we'll take it and we'll change the code, or we'll write another function that does it using recursion. So that way you can sort of see the difference between the two. So let me do this, and we'll go over to Eclipse. All right, so I have a main method here. It's just a completely empty project. And let's write a sort of a regular loop factorial. So this is going to be public static, because we're in the same class as main. Any other functions that we write here that we want to call for main, of course, we have to make static. And it's going to return an int, so it'll give us back the result of this factorial. And I'm going to call this, I'm actually going to call this loop factorial. And it's going to take in one value, and this is going to be the, I don't know, we'll call it num. Which I could probably just call it n. Make it a little bit less writing for us. So to do a sum, remember what we normally do. We normally create an int, and we call it sum, and we set it equal to 0. And then in our loop, we sort of do the summation stuff. For a product, we need to, I'm going to call this prod, for our sort of variable that we're multiplying by. But we need to set it equal to 1, because if I set this equal to 0, I would just get 0 as the result, and then you'll see a little more why in a second. So let's do a for loop, and I'm just going to follow with the equations. Remember, the equation was k equals 1 to n. So rather than using I here, let's just use k. So start with k equals 1, and we're going to k less than or equal to n. We are going to include n in our calculation there, or we're going to include the value of n when we do the product, and then we'll do k plus plus. So this loop here follows exactly what you see on the slide for the equation. Go from k equals 1 to n. And all we're doing is just multiplying the sort of subsequent k's. So back here, I'm going to do prod equals prod times k. Or I could do the shorthand, of course. I could say prod times equals k. And then we'll return prod. So this is your standard sort of loop way to do a factorial. And if I run the program, let's do a print in here. And I'm going to print out a %d, let's make a variable for n here. It's n. Let's do n equals 3 to start with. So I'm going to print out n. I'm going to put the factorial symbol, and I'm going to say equals %d, and that's going to be our result of our function call, and then a %n. So I'm going to put here, I'm going to put n, and then I'm going to call loop factorial and send in n. So we're going to put n in the %d, first %d, and the result of loop factorial of n in the second one. So when I run this, we get 6. So 3 factorial is 6, and that should make sense. 3 times 2 times 1, that's 6. We can put in 5. I think 5 was 120 if I remember correctly. So yeah, so we get 120. So it looks like it's working properly. You should assume that the number is greater than or equal to 0. This does work for 0 as well. This gets the correct result. 0 factorial is actually equal to 1. So that's something to remember. So this works perfectly fine. There's absolutely nothing wrong with doing it this way. Recursion is going to look very different than this. There will be no loop, but we will still get the same result. So if on homework or on something in the future or on an exam or something, you have to write a factorial method, the loop way is probably the most natural way to think about it, especially because we've been using loops ever since CS1. Recursion, on the other hand, is a way that you program where you call the method within the method itself. So the method refers to itself to solve the problem. This is never necessary. It might be less code, so you might end up doing sort of overall less typing to write a recursive algorithm, but you never need to do it. You can always write a recursive algorithm as a loop. So basically sort of what you just saw. So like I said, in some situations, it might be simpler. It might be easier to write code. It might be easier to understand code. But there are downsides as well. It can be more expensive in terms of memory. So it might take more memory. There's various reasons for that you'll sort of learn about more in the future. And it might actually be slower. The domain that I came from, the sort of science and sort of physics programming domain, we never used recursion because we were always worried about speed and memory usage. And so since recursion can be worse in those two aspects, we would never use recursion. But in sort of everyday code, it can make things easier for the programmer. So let's think about this factorial problem in sort of a slightly different situation, or sort of a slightly different way. The sort of minimum factorial you can do is 0 factorial, and that equals 1. And we saw that when we ran with 0 factorial. This is what's known as a base case. We'll talk about how the base case is used here in just a second. Then we can define a factorial as a different type of equation, not using a product, but using a factorial itself. Right? So if I wrote down 5 factorial, that's the same. So 5 factorial is exactly the same as 5 times 4 factorial. And you could keep going with this. You could say that, all right, well, then we have another factorial here. So we can say 5 factorial is equal to 5 times 4 times 3 factorial, and so on. And then you get all the way down to 0 factorial, which was just equal to 1. So, right, so you just keep going. 5 times 4. I'm going to skip a few of the steps here. Times 3 times 2 times 1 times 0 factorial, which is just 1. So technically, I would have 5 times 4 times 3 times 2 times 1 times 1 to get my result being 120. This is the idea of recursion. I'm using basically the process I'm using here to solve this problem, 5 factorial, uses a slightly smaller factorial to help me solve it. And then when I want to get 4 factorial, I use a slightly smaller problem here to solve it, and so on, all the way down to the base case. So as far as programming this goes, it's just an if-else. That's all it's going to be. So let's go into Eclipse and actually code this up. And then I'll sort of run you through exactly what's happening in sort of a pop-up thing on the slides. So I'm going to write a separate function. So we'll have our loop factorial, and then we'll have our public static int. I'm going to call this. I'm going to call it I guess I'll call it like the R factorial. And we still take in an int n, but in our actual function itself, like I showed, it's just an if else. We have an if and we have an else. The first part of the if here is the base case. If n comes in as 0 with 2 equals, if n comes in as 0, we just return 1 because n or 0 factorial equals 1. That's it. That's all we got to do for the base case. In the else, we return. I'm going to put some parentheses here. Actually, let's leave the parentheses out just so it's hopefully a little bit less confusing. We return n times another call to R factorial. And this time we send in n minus 1. So this is the recursive step. Because remember, our sort of total equation was n factorial equals n times n minus 1 factorial. That's exactly what we've done here. I send in an n factorial. I send in an n for doing the factorial, and I return n times n minus 1 factorial. So in my function, it's calling itself. When you do that, you make a recursive function. Now, yeah, it might seem kind of weird. Like, okay, I'm returning another function call, but remember what happens when you do a function call in a statement like this. It runs this function next. And then when it runs that one, it hits up here, and then it runs the function again. And then it runs the function again until we get to the base case. So let me show you, in the slides sort of what is happening here. And then we'll do some stuff in main. So originally, let's say you wanted to do factorial of 4. And I have my function named slightly differently here, but let's say you wanted to do a factorial of 4. So in main, you would call factorial 4. Well, in that function, you would return, remember we had n times factorial n minus 1. So that would be, you would return 4 times the factorial of 3. But we have to run this function now. And so that's the next thing in this call stack. So all the method calls are sort of stacking up like this. So we call factorial of 3, which is just 3 times the factorial of 2. But now we're calling factorial 2. So now we got to do 2 times factorial of 1. And then we do factorial of 1, which is just 1 times the factorial of 0. And then we hit the base case. So in our method, we hit, return 1. So now the call stack collapses back down. So we stacked up all of these calls to factorial. And then this call stack collapses back down to main. So I returned 1 here. What does that mean? This 1 goes to here. So in my little pop-ups here, that's exactly what happens. We get a 1 there. And then we're returning 1 times 1. Well, that's just going to be another 1 here. Then I'm returning 2 times 1. Well, that's going to give me 2. Now I return 3 times 2. That's going to give me 6. Comes down to here. And then 4 times 6 finally gives me 24. So that's the sort of basic idea of how this sort of calls build up. You always think of it, let's just go through it quickly sort of one last time. You think of it as, All right, I call factorial. It's going to call factorial itself. And then this calls another version and another version and another version, and finally to the base case. And then we do all the returning all the way back down. This is why it can use up more memory, for example, because I'm sort of have to keep all of these function calls in memory. So it does take up more memory than if you just use a loop. And then, of course, it comes sort of crashing back down to main. So that's how recursion works. And you can do a lot of interesting things with recursion. We're going to do sort of a bunch of little exercises after I sort of finish talking about the factorial version. So hopefully that makes at least a little bit of sense as to how that works. Again, it's not something that you ever have to use, but if you see a function calling itself, that's a recursive function. Let's go back to Eclipse. And up here in main, rather than using loop factorial, let's use the R factorial. So we send in here. If I send in 0, of course, as you might imagine, this will give me 1. So we still get that sort of correct result. That's exactly the base case. And then if I put in 3, we should get 6 out of this. That's put in 5 else here, and so on. If you put in too large of a number, you'll likely have an issue with it. And there's various reasons for that. Part of it is that you're either going to crash if you do too much recursion, or you're potentially, for the factorial, get a weird value. This is because of the limit on the size of the integer, and if it crashes, there's a stack overflow. So we'll talk a little bit about some of that in the future. But for now, know that for relatively small values of n here, it will work perfectly fine. All right, so go to the slides. In general, you can use recursion when you can break a problem into small pieces, and those small pieces are the same as the original problem. That's exactly what the recursive one is. N factorial is just n times a smaller factorial. So typically that's sort of what you look for. If your problem can be broken into pieces and each of those pieces is the same or close to the same as the original problem. Always make sure to have a base case. Base case is kind of when a problem becomes too small, where there's nothing else you can do to sort of break it up, like a 0 factorial. There is nothing after that. There is no negative factorial, at least in the way that the sort of factorial standard is defined. There's no negative factorial. So a 0 factorial is the smallest sort of piece you can have, and so that becomes the base case. So let's do another, perhaps even simpler one. We're going to write mind blown, or whatever sort of print you want to do, n times, but we're not going to use a loop. If we wanted to use a loop, that would be a sort of a CS1, first couple weeks of CS1 style thing. But without using a loop means we got to use recursion. So let's think about that. So I'm going to get rid of the factorial stuff here, just so we just have one function to work with, and not have a bunch of other stuff in here. And I think we will keep our n. Let's keep n. Let's just pick a value of n. This is how many times we're going to do the print. I'll make a public static. This is just be void. We'll just do the printing directly in the function, and I'm just going to call this print. That's going to take in the value of n. All right, so let's think about how we might go about this. Obviously, at least one of the pieces here is going to be a call to print again. That's how we're going to make this recursive. Let's outline it in the same way we did with the factorial. Let's make an if and an else. There's a slightly more compact way to do this, but I want to sort of do it in the same way that I showed you with the factorial. So let's say n was 0. That's essentially the base case. That means I don't want to print it at all. So if I put in a 0 in here, I really shouldn't do anything. Nothing happens if n is 0. No printing. If n is not 0, then let's call print. But what value do we want to send in? That's the question. We should probably send in a smaller value of n, because at some point I want to hit this base case. I want it to hit n equals 0 so that we get that call stack collapsing back down. So I'm going to say n minus 1. Now I haven't actually done the printing yet, so let's actually do that. I'll just put it in here right above the print. You could put it after. We're going to look at an example where it sort of changes the actual behavior, whether you put like a print before or after the recursive call. But for here, let's just put it before. So I'm going to say system out printf, and we'll do the mind blown. All right, and then let's call this prints, and I'll put in n. And we get mind blown, in this case, 5 times. So that's what I put for my n. So again, the problem is getting smaller each time. So say I want to print 5 times. Well, that's just printing once and then printing 4 more times. So that's why this print 1 time and then print 1 time less in my recursive call. Eventually we get to n equals 0 and then we don't do anything anymore. That's kind of like our factorial n being 0 as well. And then everything sort of gets, then that one finishes, and then we finish the next one and the next one and the next one and so on. And every single time we had done the printing. And so the call stack collapses. So this, just by looking at it, might seem more difficult to come up with than just a loop. Obviously a loop sort of know how to do. But overall, you can write this in a very compact way. I don't need to have the if-else like this. That's just the way that I sort of normally think of a recursive function when I sort of don't know exactly how to approach it. But for example, we could change this. We're still going to have these 2 lines, but we could actually do it with just an if. So I could take these 2 lines, I could put them up here in the if, and I could say if n is greater than or equal to 1, then do this. And it will work the same way, because the else here would be the 0 condition where it doesn't do anything. And as long as n is greater than or equal to 1, we'll still do the printing. Or you could just use greater than 0, whichever you want. So it's going to do the same thing. It's just we just made it a little more compact. So hopefully this at least a little bit makes sense. We're going to take a look at a couple other versions that will hopefully maybe solidify some of this to make you sort of realize that, oh yeah, it's really just most of these are just an if else, and then you sort of think about what's the base case and what's the recursive step actually look like. So, and then I also have the code here. This is the compact version. All right, so let's do a power. It's going to take two integers, a base and an exponent. So 2 to the 5th power or something, right? So the base is 2, the exponent is 5. So it's going to return base to the exponent. But using no libraries, we're not going to use math.pow. In a regular situation, you would, of course, but let's see how you do it recursively. We're going to assume the exponent is non-negative, because that does complicate things if we want to have a negative exponent. All right, so I'm going to get rid of my print function here, and we're just going to write a function for power. Say public static. This is going to return an int. We're just going to deal with ints here, not any doubles or anything. I'm going to call this power. And so we're going to take a base and an exponent. So I'm just going to call it exp. All right, same situation as before. We're going to have an if and an else. And I'm going to use the base case in the if here. This will be the base case. All right. If the exponent, and then this is where it can take a little bit of thought. If the exponent is equal to 0, what does that mean? So if I have, let's see, let's write it like this. If I have 2 to the 0, what is that? That's 1. If I have 3 to 0, what's that? It's 1, and so on. So if I have an exponent of 0, we can just return 1, almost like the factorial version. In fact, this is basically the same as the factorial version. So we can return 1 if the exponent's 0. For all the other cases, for the recursive step, we need to return something else. So let's think about what it means to write like a, let's say 2 to the 3rd power. Well, that's just 2 times 2 to the 2nd power, which is just 2 times 2 times 2. And you can do this for any version. The key here is to say something like 2 to the n is just 2 times 2 to the n minus 1. And then, of course, the 2 could be whatever number you want. It doesn't have to be 2. So that's this idea here, which is, again, almost the same as a recursive version. So I'm going to take the base times power, base, and exp minus 1. So that's my recursive step. I take my larger problem, 2 to the 3rd or 2 to the n, and change it into something where I have a slightly smaller problem, a 2 to the n minus 1. So let's get rid of my n here, and we'll call power. Let's do a print. And I'll just print out the result. So %d and the new line. And then we'll do power, we'll say 2 and 3, and make sure that that actually works. All right, so 2 to the 3rd power is 8. 2 times 2 times 2. And of course, any values that we want to put in here, we can, and everything here should work just fine. So again, this is never required, and I want to make sure to sort of stress that. But if you find a problem where it's given, so you can look up sort of various math equations. If you find a math equation that's, say, given like this, where you have some n and then some n and then equals something and n minus 1, that's very easy to turn into something that is recursive. So this does have a lot of applications, particularly in sort of being able to convert a math equation easily into code. So let's do one that's a little bit more complicated than this. This was very similar to the factorial one. So let's do one that's a bit more complicated. A couple slides here. I have that sort of version that we just did. Here I didn't use brackets for stuff, so I don't have like the else and everything. It's just the if and then the recursive step. This is just another way to sort of simplify and make it a bit more compact. So let's do one where we print out some digits. So we're going to write a recursive method that outputs each digit of an integer to the screen on its own line. Here we're going to start with the most significant digit, so we're going to start with a 1. So we tried to put in 1, 2, 3, 4. We're going to get out 1, 2, 3, 4 on its own line. No loops. There'll be a little bit of math. That's it. So let's think about how that's going to work. So let's just keep, let's keep this, but I'm going to have this be void, and I'm just going to say have it be print, and we're going to take in a number. And in here. And here we're just going to call the function, because I'll just print directly in the print function. All right, so like normal, we're going to start with an if. We're going to have an else, so that we have our base case and a recursive step. All right, so let's think about the base case. What if n is less than 10? Then we can just print that number, because there's no other digits for us to print. So if I put in a 2, I should just print 2, and then that's it. So it can be non-trivial to think of a base case. It can take time to think of it. You might have to try a couple different base cases, but that's the simplest problem we can do, and that's usually what you look for. What's the simplest sort of version of this problem? Well, let's say if we put in one number. We're just going to print that number and be done. So let's put in here, let's say if n is less than 10, then we're just going to print that number. We're going to print a %d, %d, and a %n, and it's just going to be n. That's it. That's the simplest situation. Simplest. Let's do. It's going to be the sort of smallest problem. So something like that. Now the recursive step is going to have a little bit of math in it. So let's create an int, and let's call this like the let's say this is the. Think of a good name for it, so it'll hopefully make sense. Let's just call it val. We'll just sort of leave it at val, and I'm going to do n divided by 10. It's an integer division, so let's say n comes in as 100, right? Just as an example. Let's say n is 100. So then this val is going to be 10. So we're reducing the size of this number. That's something that we need to do, something that we absolutely need to do, because the number eventually needs to be less than 10. So we divide by 10, we're essentially getting smaller and smaller numbers that we're going to be dealing with. Now I'm going to call print again. I'm going to call print the print function that we're writing, and I'm going to send in val. So I'm going to send in a smaller number in the recursive step. After the print call, then I'm going to do a printf. And this is going to print out %d, %n, similar to before. But this time it's going to be n mod 10. Remember what mod does. So as an example, let's say n was 101. Then n mod 10 is just going to be 1. So we're going to think about where this needs to be printed. I'm printing it right now after the call, and we'll see what result we get. Then I'm going to move it to before the call and show you how that differs. So we've got our n divided by 10, which is what's going into print, and we have our n mod 10, which is what's actually being printed out. So let me do print. Let me put in the 1, 2, 3, 4. Run that. And there I get 1, 2, 3, 4. Let's think about why. When I send 1, 2, 3, 4 in here, obviously we're going to hit the recursive step. And we're going to divide by 10. So I'm going to write that out over here. So in our first call, so let me give this a 1 here. In our first call, val is going to be, we're doing an integer division, so it's going to be 1, 2, 3. And n equals 1, 2, 3, 4 coming in. So in our first call, val is 1, 2, 3. We send that into our second call. We haven't done any printing yet. We're sending it into our second call. Val will be 1, 2. We'll send that into our third call because we're going into print again. Val will be 1. And then we send that into our fourth call. What do we print in the fourth call? N's less than 10. The thing that came in was less than 10. Val came in as 1. And so now we print 1. That's why we get the 1 printed first. Now we're going to sort of work our way back because we don't call print again. We're going to work our way back. So now we're done with the print here. This comes up to this one. Well, we printed one, so we're going to come up to this one. Now we do our do an eraser here. We print one from our version here. We come back to print. We use n. We don't use val. I'm not printing val mod 10. I'm doing n mod 10. So think about what n is for each of these. So n for the first call was 1, 2, 3, 4. N for the second call was 1, 2, 3. N for the third call was 1, 2. N for the last call was 1. That's why we printed the 1. So we come back up here. We do n mod 10. What is that? That's a 2. So we're going to print 2. Then we come back up to this one. We have 1, 2, 3. So we're going to print 3. And then we come back up to this one, the original n, we're going to print 4. So that's the order in which things happen here. So it's that same idea of this call stack building up and then it collapses back down. I sort of wrote it in the reverse way here. This is not necessarily easy to figure out, not unless you're sort of used to how recursion works and sort of work with it a lot. Even to me, if I see some sort of complicated recursive algorithm, it can take me a while to figure out exactly how it's working. But keep in mind that essentially in this case, we're sort of stopping here every single time and then moving on to the next version and the next version and the next version. And it's not until we hit the base case that we do the rest of the printing stuff here. Now, let's think about what happens if we move this print above the call to print. So let's think about how that works. So let me draw this out again. So if we come in our sort of first sort of version of this, we're going to have n equals 1, 2, 3, 4. Val is going to equal 1, 2, 3. And we're going to print right away. We don't call the print function until after we do the actual print. So here we're going to print n mod 10, which is going to be 4. N mod 10 gives us a 4. Then we move to the second call, a print. Here, n is going to be 1, 2, 3, because that's what val was. And val changes now to 1, 2. And we print n mod 10, which is 3. We move to the third call, where n is now 1, 2. Val is now 1. We print 2, n mod 10. And then the fourth call, n is 1. And that's it. There is no val because we're now less than 10. So we're done with that one. We do our print 1. And then it's going to fall all the way back down, but nothing happens after this print here. So we don't do anything else. There's nothing here. So yes, it sort of goes back down the tree, but there's nothing else to do. So we should see a print of 4, 3, 2, 1 if we run this version. Let's do that. So now we get it in reverse order simply by moving where the actual printf was. Again, this is not necessarily something that's sort of easy to figure out the first time that you see it. But keep in mind that these things are important, where you do things either before or after the recursive call itself. The rest of this is just doing a little bit of math. So in the slides here, I do have the sort of calculation for this. In the slides, I didn't put an extra variable. I just put the n divided by 10 directly in, but I sort of wanted to be able to show what that was when I wrote it out. And then the next piece of this exercise is, do it in reverse order. And that's what we just did. All we had to do was move where the print was. And then we were good to go. So it's very easy to change that when this stuff happens in a recursive algorithm. If we were using a loop to do this, you would have to change the sort of the definition of the loop, sort of how you wanted to do it, or change the math inside. I didn't have to do any of that here. I just moved where the print was, and it works. Okay, I think I have one more. I think this is the last one, if I remember correctly. We're going to do the Fibonacci sequence. So if you look this up on Wikipedia, this is one of the equations that it has, and it's perfect for recursion. We're saying if we send in an n into this function, the result is just n minus 1, that same calculation, the same f, n minus 1 plus n minus 2. Because we have an n minus 1 and an n minus 2, we actually have two base cases. When we send in a 0, the result is 0. When we send in a 1, the result is 1. So this is the recursive version, or the recursive equation for the Fibonacci sequence. And so you're going to see something like this. You can see 0, 1, 1, 2, 3, 5, 8, 13, 21, and so on. It's just the sum of the previous values, right? So 1 and 0, those are the base case. So 0 plus 1 is 1. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5, and so on. So that's basically how you're building this up. So let's write a function that does this. So back in Eclipse, I'll get rid of the print one here. And we'll write a function, public void fib. Actually, we'll have this return an int since we're going to get a value out of it. And we're just going to send in n. And actually, this should be static here because we're in the same class as main. All right. So we're going to send in n. This will sort of be the number. So the first number is the 0th number. The next number is the 1 number. So think of it as sort of like array indexing from the slide previous. So we have two base cases. So I'm going to put an if. I'm going to put an else if. And then I'm going to put an else. So in here, the first if here, I'm going to call this base case 1. The else if is going to be base case 2. And then we'll have our recursive step. So base case 1 is if n is exactly equal to 0, then we just return 0. If n is exactly equal to 1, we just return 1. Those are two base cases from the equation. It's just this. If n is 0, we return 0. If n is 1, we return 1. All right, for the recursive step, remember what this was. This was f of, I'm going to put sort of parentheses here for it, but I'm going to say f of n minus 1 plus f of n minus 2. So that's our sort of equation here, and this would be f of n. So that's what our recursive step is directly from the formula. So all I have to do is return fib, another call to fib of n minus 1 plus fib n minus 2. And that's it. That's the Fibonacci sequence in recursive form. And the nice thing is the math equation made it really easy to write this up. The math equation was already in this form for us. We just had to write it out in some if statements. So that's one of the really useful things about recursion, is if you can find an equation that is in a recursive form, it's super easy to program up. So let's do a print here. And let's do prints, and we're going to print out a %d and %n. And then we'll say fib, and let's put in like 4 for this. So I run this and I get 3. So let's go back to the slides, make sure that's right. So we have 0. We send in 0, we get 0. So that's a 0. It's like I said, sort of the array indexing. So 0, 1, 2, 3, 4. That's the one we just did. So if I put in 5, I should get 5, and 6 should be 8. So we can check to make sure that it's all working. So let's put in a 5 and a 6 and just make sure. So put in 5, run it. There's 5, and then the next one, 6, should be 8. And sure enough. So it looks like it works great, and it was super easy to code up. If you do this in sort of a loop way, it's going to be relatively complicated to think about, because you have to store the previous 2 values that you had and then add them together as you're going through the loop for as many values as you need. So it's one of those things where it's probably a little bit more time consuming to think about the sort of way this needs to work in a loop, whereas with the recursive equation, with the recursive math equation, it's super easy to just throw in. All right, and then of course I have that here as well. All right, so just think of recursion as an alternate form to do a repetition without a loop. So don't think of it as sort of some crazy thing that you only use in certain circumstances or something. Just think of it as a different way. A different way to do it, which may or may not be sort of easier to think about. Recursion does have substantial overhead. Every time the program calls a method, the system has to assign space for all the variables and all the parameters and all the stuff associated with the function. So this can use up extra memory and extra time to manage all that stuff. So again, from the sort of the scientific space where I came from, we never used it because we were worried about memory and time. If you do too much recursion, then you can exceed the call stack memory. So remember how I showed you the stack sort of building up and then collapsing back down? If you have too large of a stack, then that's one way to cause a stack overflow. We can see if we can create one. Let's see. Typically, the stack memory is sort of limited on the order of like megabytes. So it shouldn't be too hard to do, but I don't have an easy example at the moment. Let's see if we get something here. So like our Fibonacci sequence of like 10,000. We'll see if this causes us a problem. It is going to take some time to do because it's calling it. I mean, we're literally calling the Fibonacci function here 10,000 times. So we'll see if this gives us any sort of issues as I finish up the slides here, or if it even finishes. We'll see. All right, so you may have seen the website Stack Overflow and stuff. That's where that name came from for the website, was from this exceeding the call stack limit. It's not something you have to worry about too much right now. You'll learn a little bit more about sort of stack versus heap memory and all that kind of stuff later on. But just know that if you do too much recursion, it can cause a problem. So the overall sort of take-home message here is that a recursive method is just a method that calls itself. So that can be useful. It might be easier to write things in a recursive way than a loop way, or the other way around. Again, we're used to loops. So it's going to oftentimes be easier to think about how a loop's going to look rather than using recursion. But if you see recursion in the future, or if you want to mess around with some recursion in the future, just think of it like this: base case, recursive step, and make sure that you can break your problem up into smaller and smaller pieces. So recursion, again, is just the alternative to looping. Sometimes it's simpler to write, but that comes at a computational expense and is sort of more limited in depth. In other words, calling a function 10,000 times is a bit more expensive than looping 10,000 times. You'll oftentimes see that kind of trade-off in computer science, where if something is easier to write, it might use more resources, or if something's more difficult to write, it might be faster. Something like that. Usually, you'll see that's those sort of trade-offs all the time. So let's go back and just take a look real quick here. Yeah, so this is still running, so I imagine this might be running for a while. So I don't want to sort of have to worry about sort of sitting here over that for that stuff, just to see if we can get it to crash. So that's all that I have for this lecture. Next time, we'll talk a bit more about the JCF. I want to talk a bit more about some of the different types of data structures.